Okay, good evening everyone. This is week 11 of Essential of Data Science with R software, sampling theory and linear regression analysis. I am the TA of this course, Kamna Mishra from School of Mathematical and Statistical Science, IIT Mandi, and this course is basically instructed by Professor Salam, who is from Department of Mathematics and Statistics, IIT Kanpur. Okay, so these are some useful links regarding the class. So move to the main points. Okay. So in the last class, we have just started what is multiple linear regression analysis. So what we have started was that when we use let me just go through that slide. Okay. So what we have seen is that when we have a simple one, okay, so when we have simple linear regression analysis, we have one dependent and we have one independent parameter. However, when we have multiple, so by name multiple, we have multiple uh, independent parameter, not multiple dependent parameter. So that is one thing we need to know, that we have multiple uh, independent and one dependent parameter. So there will be one parameter which will be depending on all others. Okay, so the next is that how do we formulate it? So to formulate it, uh, just a minute. Okay. So for to formulate it, we have used this equation, which is given by y is equal to x1 beta 1, x2 beta 2, and xm beta m. So here x1, x2, xm, y, all are the values, all are the data which we will put into it, and the beta 1, beta 2. So basically all the beta i's are the values which we want it to give us to us. And now epsilon is the error, the random error which is gonna happen, because uh, uh, even if you take just y is equal to x1 beta 1 plus epsilon, so the cases we are taking here, it is not that all the points are lying exactly on y is equal to mx. So all the points are not lying exactly on that uh, line, all the points are not lying exactly on that line. So that is why there will always be some error, but we want these parameters, these beta i's, in such a way that we can minimize this error. Okay, so here we have observations, here we have a response variable, and at the end we have the explanatory variable. Uh, so this is for y. These are capital X1 up to xm, let's say. So we have here for y1. So let's say there will be one value of response variable, and for that there will be m value of independent parameter. And again, so for let's say we can have some 3 to 4 independent parameter, and we can have some 20 to 30 or so on, like 500,000, these values. So that is up to how much we have gone through. Now the further part is basically like whatever we have done in the last class. The further part will be almost same. Okay. So in last to last class, so firstly what we have gone through, we have gone through what is uh, So whatever we have gone through for simple linear regression analysis, we will have all these things for multiple linear regression analysis. So firstly, we want to find these parameters. So for beta i's, so to find these parameters, first we have used two methods. First one was least square estimation. The second one was maximum likelihood estimation. In least square estimation, we have used the ordinary one. The other one is weighted least square estimation, which we have not used here. So for multiple linear regression analysis, we are going to do the same. There will not be any change. So we are gonna firstly see what is ordinary least square estimation for multiple linear regression analysis. The next thing we will move to, after finding the beta i's, what are the properties of these beta i's. So if we want to estimate them, the estimates of beta i's, are they biased, are they unbiased, or what is the variance of it? It are these parameters have minimum variance all over the estimates? Like we can find a lot, there are a lot of ways to find.
जैसा फिर चेज करते टाइम ना अगर गेम चलता
So in ordinary least square estimation, we for multiple linear regression analysis, we will do the same, just we have done for the simple linear regression analysis, and we will go through each and every properties which we have gone through there. Next, we will try to find that confidence interval for the estimates, and after that, we will see how to find the estimate using maximum likelihood estimation, and is it like same? So is the estimates of found by maximum likelihood estimation same as least square estimation, uh, or if there is any biasness, and what is the difference with the variance? Okay, and at the end we will see how we can do all of these in the R software by taking one example. Okay, so in the last class we have just introduced the multiple linear regression analysis, and we have seen that we can give it by this particular formula. Uh, okay, by this particular formula. So today what we want to do is that we want to uh, we want to now estimate these beta i's. So j- l- like in this, we are not going to have the proof, but it is same whatever we have done in uh, this me show you simple integration. Okay, so just the method is least square estimation, and what we have done firstly to find these estimate, we wanted to minimize this random error. So to minimize this random error, what we have done, we have taken the first derivative of this and then second derivative of this, and we have found the b naught and b1 from that. So now when we try to find b naught and b1 from here, so uh, uh, all we need to do again is that find the first derivative and find the second derivative, and that second derivative needs to be uh, greater than 0, so that we can say that it minimizes it. So here uh, we had this result beta naught beta 1 and the Hessian matrix, so the double derivative uh, was greater than 0, so we have said that it was minimizing it. Okay, so um, basically we are not giving the proof here, so we will just move to the estimate part. So the line we have is x1 beta 1 x2 beta 2 So here also our objective is same. We need to minimize this error in ordinary least square estimation. Okay. Uh, so here rather than giving just p naught p1 and up to pm, because we have no idea for how much, because how much parameters are there. Okay, so if I will put bm is equal to let's say 3, then we need to take three first derivatives, and if I will take 4, then we need to take 4 derivatives. So we are not going to do it like this. So the simple method is that, so we have the result for it. So the OLS estimator of these beta. Okay. So uh, we can write this one like y is equal to x beta plus epsilon. So when we need to minimize it, we will write it as y minus x beta. And from there, when we try to solve it, we can write the OLS estimates of these beta. Uh, okay, so we can write it by this. And uh, so we have two estimates. So first one is for beta naught, beta 1, and the sigma square in the simple linear regression analysis. Here, just for all the beta. So this one is not just one expression. So you need to remember, when I'm writing this x is basically containing this x1 x2 up to xm. So this is not just one x, this is a matrix. So this x is a matrix, and this one is a matrix, and at the end this y is one matrix. Okay, so there are three matrices. Okay, so it's inverse, and at the end it is some 1 by some n by 1. So at the end we will have more, I think this one is m by n. So at the end we will have some m by 1 matrix. So we will have the beta. How many betas are there? M, right? So we will have beta. Uh, Let me write this. So at the end we will find this beta as m by 1 matrix. As this is n by m, so at the end we will have this m by 1 matrix, and these m by 1 matrix will be the estimator of beta i's. So this one will be for beta 1, for beta 2, and up to beta m. So these are all the estimates. So just because it is written in the simpler way does not mean it does not contain all the information. Okay. Okay. The next thing is that we have the for maximum likelihood estimator, we have seen in the simple linear regression analysis that the estimate of MLE is same as OLS estimates, but its variance is different. So here we will see what is the estimator of sigma square, and then for MLE we will see what is the estimator of sigma square, and we will see whether they are same or not. Okay. So its estimate is 1 upon n minus k what y minus xp transpose multiply by y minus xp. So these are also the metrics. So we are taking one matrix transpose. So basically A transpose A. So this is the estimator of sigma square. Okay. Uh, okay. The derivation is, I think, given in the class. So you have gone through that, and all you need to do is that, rather than this, what we have y minus x beta, we will write it in terms y dash y transpose y, so that it will make it easy to do the derivatives and all. And then we will not have the terms like beta 1 beta 2 up to beta m, because we do not know up to what m we have in the real life or we have for our modeling. So that is why we are just writing in this form, y x transpose x. So when we write in this form, so it can contain like whatever uh, number of variables it needs. Okay. uh, Okay. The next thing is that we want to, so for when we do these all these things in R, what we do firstly, we firstly fit the model. After fitting this model, so once we got our regression model, we have the fitted regression values. Okay, so the fitted regression model is y is equal to bx. So b is our estimates we have found for our regression model, and the fitted values for these given x. So there will be some real values which are given by y, and there will be some fitted values uh, for this x, and these can be denoted by y bar xp, and it can be written as x transpose x inverse dash y, and we write it as h. So here we have found our y as x bar x transpose xy. So uh, I have just written this b, the estimate we have for b. So I have just put this value x bar x transpose, sorry, inverse x transpose x inverse into x transpose multiply by y, and this whole value is written as h, and we call this as head matrix. So after fitting the model, this is what we have. Now, this matrix will have some properties, and the properties will be, the first property is that it is symmetric matrix. So, what is I hope you all know uh, the symmetric matrix. So symmetric. So basically, symmetric matrix will be, it will have these diagonal, and whatever values we have here, the same will be here. Okay, just a minute. There is power coming. So, okay, okay. So what I was saying is that. not this. Okay, this one. Yes. So we have this symmetric matrix, and symmetric matrix have this property that we have one diagonal, and this what are the whatever the values have here will be here. So basically, aij will be equal to aj I. Okay. So obviously when I and j are same, so when it is 1 1, so obviously it is equal to 1 1. But when it is not, so a 1 2 will also be equal to a 2 1, and a 3 1 will be equal to a 1 3, etc. and etc. Okay. Can you hear my voice? Hello? Am I audible to you?
Yes, yes, yes.
Okay. Okay. Uh, see if there was any change. Okay. Cool. Okay. So, okay, so what I was saying is that we have this property for symmetric matrix. The next property we have is that this is idempotent. So idempotent matrix have this property. Uh, H basically H is square we say, but since it is a matrix, we are just writing H. So H square is also fine. H square is equal to H. And the third property it have is that the trace of h, so when we try to find the trace of h, what will happen, if you will try to write this, so uh, the a b inverse is what, b inverse a inverse. Okay, so if I will put it here, what will happen, it will be x inverse x transpose inverse and then x transpose. So a inverse is identity, and x transpose inverse x transpose will also be identity. So these both will be identity. So at the end what we will have, it we will have a identity matrix. Okay, so trace of h is nothing but trace of im, which will be equal to m. Okay. Uh, the next thing is that when we will take this h bar, which is I minus h, then this matrix is also symmetric. This matrix is also uh, it will have the same properties as h. So it is symmetric. It is idempotent. And the next and last properties, its trace is n minus m, because the trace of I is n, and then for and trace of h is it is m, so it will be n minus m. Now why we need this, we need h bar to find our residues. So uh, in the time of fitting model, what we do is that firstly we fit the model and we try to find the parameters. The next thing we do is that what are our fitted values and what are our real values. The third thing we see is that what is the difference between fitted values and real values, because if the difference is so much, then uh, it may be not fitting it real well. So this h bar will help us to find the residues. Okay, so what are the residues? It is like just error, so it is y. Now this one is basically, sorry, not y bar. Okay, uh just one second. So when we have y minus y bar, we have y minus xb, and then we will write the b, uh, xb. So xb we have found from here, y cap xb can be written as hy. So here, it the y is also a matrix, so we can just multiply it. If with identity, then it will also be the same. So I y will also be same as y, right? So what we can do is that we can take out the y from here, and we will have I minus hy, and this I minus h can be written as h bar y. So these are the our residues. So after fitting the model, we have found our residues and that uh, fitted values. Okay. Okay, so now what we will do is that we will try to find this in our software. Okay, so let me open the file of last week. So week 10. Okay, so here I have taken two more variables. Okay, so let me just remove all of this. Notes. Okay, so till now, what we have done is that we have taken one variable as number of balls and other variables as number of runs. So number of runs are dependent on number of balls, but number of runs are also dependent on, let's nd, that number of day he practiced, and there is np. So we have given some score, some previous score. So something like what are the chances of this cricketer winning that, or doing good on that particular ball. So that also matters, because if he is not doing so well in that, then we cannot expect him to just give all the balls, right? Okay. So next, like before going to um, fit that, we will do some analysis just for these. So we will see that how they are correlated, and what is the correlation, and what is the scatter plot between them. Are they increasing with itself, or are they decreasing, or is there any other relation? So what we have is that we have an r. So let's say an r I'm denoting as y, so that it will uh, look more clear that this is our y variable, and these are our uh, independent variable. So this is the dependent variable, these are independent variable. Okay. uh, Okay, so here is our scatter plot, and uh, this is with respect to NP, NP, and NT. So this is now symmetric. Okay, so you do whatever is here, it is here. Whatever is here, uh, so it is 1 3. So it will be here. It has to be here. Let me just see. Or is it opposite? No. So it is y and r. So okay, so these are in the opposite, just axis is rotated. Okay, because here it is 5, 10, 15, 20. Here it is 5, 15, and in that way. So this axis is rotated. So this is between, let's say, in the x-axis we have nb, in the y-axis we have y, and here in the x-axis we have y and r, and here we have in the y-axis we have nb. So that is the only difference. So if you will see, these are just rotated in this way. Okay, fine. So now, if I will just see the upper matrix, or like upper triangular matrix or lower triangular matrix, it does not make any difference. What we need to do is that, what we need to see is that here we can see some, if we will try to fit some line here, then it is somewhere increasing. So with the number of balls, number of runs are increasing with NP. So NP, you can see that it is not so clear exactly. Somewhere there is a line where it is increasing, when somewhere it is at very less point. So previous score is not very good, but now the cricketer is doing very well. So this is something like this. And the number of days he practiced, so here also there is something like some line can be here, but there are two three exceptions that they have not practiced so well, but also they have uh, played well. Okay, yeah.
How we are changing the axis, there's number of runs and overs, balls.
Okay, so I have just given it the command, and I'm not changing the axis. What it was doing is that it makes the scatter plot in such a way.
Okay.
Okay, so here it just so I will,
Follow the command.
if
Okay.
I will say you that make the scatter plot of x comma y. So here it makes x y, and here it make for y x. So whatever way you want to look at, the result will be same for that. Okay. Uh, so okay. The next thing is that, so here this is the scatter plot. The next thing is that what we can have is that we can have the core plot. So how they are correlated. So there is one thing we can just find the correlation, but that we need to do one by one. So rather than that, we can have this core df1 also, but let us visualize it. So for that we can use the core plot. Okay, so these are all things whatever we have done, I think, in first or second class. So in first or second class, we have gone through the graphics of data frame. Okay, so here, uh, let me define just this variable. Okay, x1, 2, 3, y data dot frame, and I can define it by ynr and B and B and D. Okay. Now, uh, so we have this data frame. Uh, we will plot core plot core x1 2 3 y. Okay. So I have not given here any method. So if So this is coming as a plot. If I will give just method as a number, it will show me numbers. Okay, so you can see that the number of runs are dependent on number of balls, which is zero point 0.5. uh, then it is not dependent on number of practice days and not dependent on number of days. So uh, let me do this again. Okay, so now you can see we have two plots. So sorry. So yes. So NP, you can see that I have generated just randomly. Okay, so RUnif generates randomly numbers. So when I have generated previously this number of runs, this was not uh, uh, this its correlation with NP. So number of days someone practiced, it was minus zero point zero 0.04, which is not true. Like if it has practiced, it has to do better. So let's say I have generated it again, because this is not the real data, right? So now you can see that sorry, it was the previous score. So now when I have generated this data again, so you can see that uh, it is obviously it with itself its score is 1, and with number of balls its score is 0.55, and with number of day it has practiced before, it's 0.42. And sorry, number the previous score, it is this, and number of day it has practiced right now it is 0.06, because this is again not the real data, so it is not going to give the real results. Okay, uh, but for better practice, you can generate in such a way that it will have the high correlation. Okay, so now from here, what we have seen is that these two are uh, independent, and y is more dependent on these two rather than the third one. So y is not depending on this one parameter so much. Okay, so now after having all of this, now we will perform our this regression test. Okay, so now we will have this LM and then Y and R. Okay, and then we will have this. Okay, so now you can see that these are our intercept. So our fitted model is basically minus 11.0860 plus 1.1002 x1 plus 4.8583 x2 plus 0.2787. Okay. Uh, now, uh, okay. So once we have found this, what we need again most is that what are the values it has fitted. Okay. So now this is the our real values 18, 23, etc. And our fitted values are 19.81, 516, 19.6, 16, 19 point this and this, and etc. So these are our fitted values. Uh, Next, we have residuals. So the residuals are like this. So you can see that minus 1 point this, 3.3, this one, etc. Okay. So these are our fitted values. So from the formula, it the fitted values are this, and the residuals can be found by this. Okay. Okay. So when we have the summary of it, we will see anyway later. But here from this, we can see that the intercept value is greater than 0.05. This is greater than 0.05. This is greater than 0.05. So none of these really matters to find the uh, number of runs. Only number of balls matter. So whatever data we have given, the result it came from this is that the uh, only thing matters here is that it's number of balls, not the other parameters. Okay, so we will see now. Okay, uh, okay. So the next is that properties of this OLS. So there are some properties of OLS, and most of the properties are same whatever we have in the simple linear regression analysis. The first one is that it is unbiased. Okay, so let me just write properties of OLS. Okay, okay, okay. So properties of OLSC is that the this one E B is equal to beta. So B is unbiased uh, parameter of these beta. Uh, the next property is that the covariance matrix, so VP, that will be nothing but uh, so variance. So basically, it is uh, we can have just by this p minus beta dash, sorry, p minus beta and p minus beta dash, because it is what it is, uh, xi is square minus x bar is square. So from that, because since it is in matrix, so rather than a square, we are using this one, and then sorry, this one and multiply by its transpose. So rather than a square, we are going to write a transpose. So this one is sigma square x bar, sorry, x transpose x inverse. Uh, the unbiased estimator of sigma square. So the estimator which we have given here, this one minus this is basically the unbiased estimator. So estimator of sigma square is also unbiased. So estimator of that beta is also unbiased, and estimator of sigma square is also unbiased. The next last one is that the covariance matrix. Okay, the covariance matrix can be estimated. So that this one is our covariance matrix. To estimate it, since it is unbiased estimator, we can just directly use this to estimate. So we can have this estimate. Okay. Uh, the next one is that variance of this y cap. So the fitted values. It is nothing but sigma square. Uh, so this is sigma square h, and then after that the variance of estimated, its estimate also. For this is its estimate. So its estimate is nothing but the sigma square can be estimated by this, and h is already estimated. So it will be nothing but sigma square cap h. Okay, and then the next property is that OLSC is not just unbiased, it is also consistent estimator. Okay. And then uh, S is square. So some people denote this with also with this S is square. So a small s is square. So that is small s is square is a consistent estimator of sigma square. Okay. Uh, Now, so what were the properties we have? The estimates of beta and the sigma square both are unbiased, both are consistent, and the variance of these can be given by the simple formula. And next is that next property is that what is the uh, Kramer Rao lower bound of beta sigma square. Okay, so what is the Kramer Rao lower bound? So we say that Kramer Rao lower bound. So there has to be, like, whenever we do any analysis, uh, we we know that there will be some variance. So they, if a person is saying that the variance is zero, so its Kramer Rao lower bound needs to be zero. So basically what we are saying is that if it is its Kramer Rao lower bound is zero point 0.5 and a person is saying our variance is 0.03, then it is not a possible case, because this lower bound, so it gives the lower bound for the variance, that the variance cannot be lower than that. So its lower bound is given as sigma square x x bar this 0 0 2 c and n. Okay, and the covariance matrix which we have from OLS, this so you can see that V bar, this one is sigma square xx minus. So this one is sigma square, but this one is given as 2 sigma to the power 4 n minus k. Okay, so there is n minus k division, and this comes as 2 sigma to the power 4. So what we say is that with the help of OLS, uh, OLS attains, I'm just writing Kramer Rao bound for be not for s square. Why? Because this and these are same, but this one, like when we divide by the larger number, obviously it is a small value. And when n minus k, so n minus k, the below one is the smaller number, so this one will be large. So basically 2 sigma to the power n minus k increase greater or equal to 1. So this is going to happen. So this value is our more. So basically it is saying the minimum variance is this, and the variance attained by OLS will be greater than that minimum variance always. So it has, basically we say that it has not attained the Kramer-Rao lower bound for this. Okay. So these are the properties for it. And now if you want to go through the derivation, you can go through that slides, and the derivation are quite simple. Uh, the like we have one more class uh, on 15, and on 16 there will be a revision class. So on, if you will have any confusion regarding the derivation or anything in this course, like all these for 12-week course, then you can ask in that. Okay. So these are all regarding to the OLS estimator. The next we will have is that maximum likelihood estimation. So it is in the last class what we have done is that for the OLS estimator, what we do is that we try to minimize that uh, s- is, is summation and then is squared error, residual error. For uh, MLE, what we do is that uh, we firstly try to find uh, the distribution of this error, and then here it is. Okay, so firstly we try to find the distribution. So the distribution, as we say, that the random error follows normal mu sigma square. Here we have taken from the very starting that the random error is following normal 0 comma sigma square. So the distribution it will follow will be normal, so this will be normal distribution. And normal distribution will be this expectation and then x minus mu. So the mu is 0, this one is our x, and this is square divided by 2 sigma square. Now for the MLE, what we do is that we try to find its likelihood firstly. So for likelihood, all we need to do is that if there is I two, if there is I 1 to up to n, then what we do is that we multiply its all of its PDF, but then uh, and then we want to maximize it, but maximizing it directly is very tough because of this multiplication. So that is why we take log likelihood, and then it gives us very simple this expression. And then based on that, what we do is that we try to find its derivative. First derivative, we try to make it equal to 0, and then we say that its second derivative needs to be uh, less than 0, so that we will have the maximized maximum likelihood estimation. So similar thing we need to do here, there is no change. So all you need to say is that this one will follow normal sigma square I, because there are some n terms. So for all n there is sigma square. So we will have this same expression, we will have the same everything, and then we will try to find the estimates. So I will just write uh, the likelihood function of it. So for the likelihood function of it, all we need to replace is this, because this one is the only different part there. So here our L of let's say just so this likelihood will be, so this one will be same 2 pi sigma square, and because it was root 2 pi sigma square, when multiplied by n times it will be this. And uh, the inside part will be summation epsilon I square, and in place of that we will write uh, minus y minus x beta dash y minus x beta, then 2 sigma square. So in place of this, in place of this, so it was basically x minus mu whole square divided by 2 sigma square. So 2 sigma square is remaining same, x minus mu. Mu is 0. So basically in the above there is x square. What is x here? It is epsilon I. So epsilon I square. Now epsilon I is what? We have the expression as y is equal to x beta plus epsilon. Now epsilon I square is basically y minus x beta square. So its square we have written as y minus x beta transpose multiply by y minus x beta. So this is the expression, and then all we need to do is that we need to just take the log of it, and then uh, basically do the same for find the first derivative and find the second derivative. Okay, so after finding the first derivative and second derivative, uh, uh, beta cap is same as whatever we have found in our OLSC. Okay, so this one is say this one is same, so x transpose x inverse multiply by x transpose y. So this one will be same as this, and sigma square this will be 1 upon n y minus x. Okay. So I've just denoted beta cap and sigma square cap to make it just different from OLSE. You can denote it by beta dash or beta tilde or any other way. Okay. Uh, okay. Now, uh, since these are same, so since these estimates are same, so beta cap for MLE also it will be unbiased and consistent. But this sigma is square cap, this one uh, will be equal to n minus k upon n s square. So because here it is n, there it was n minus k. So basically n minus k s square. These terms were same in both. These were same in both. So n sigma square will be equal to n minus k s square. And since expectation of s square was here, uh, when we say that s square is consistent estimator. Yes, when we say that estimator of S sigma square is also unbiased, That means we are saying that expectation of s square equal to sigma square. But here the sigma cap is square. If I take its expectation, what will happen? It will be uh, expectation of sigma cap square will be this n minus k upon n sigma square. So this is not equal to sigma square, right? Since k is not equal to 1. So we are saying that sigma cap square is biased estimator of sigma square. Sigma cap square basically found by MLE. So this one is bias estimator. Okay, so we have seen that uh, the va- uh, the estimates of parameter are biased unbiased for both the cases, whereas variance is unbiased for OLS and uh, unbiased for OLSC and biased for the MLE. Okay. The next thing is that the testing of hypothesis. Okay. So now, so testing of hypothesis is also just same as whatever we have done in the last class. So what we have done in the last class, we have assumed we have done testing of hypothesis for two. First one is B naught, next one is beta 1. Okay, so beta naught and beta 1. So here we have four. Let's say in our case we have beta naught, beta 1, beta 2, beta 3. Now, what is the testing of hypothesis? H naught is that beta naught or beta 1 all are equal to 0, and the alternative hypothesis is that uh, it one of them can be not 0. So, if you try to see here, uh, from here we can see that this one is the only for which that beta 1, so beta 1 is not equal to 0, other betas can be equal to 0. Okay, so now so we considering the null hypothesis, uh, we consider the null hypothesis as h naught as beta i's are not equal to 0, and we consider h1 as uh, beta I j, sorry, the null hypothesis is this and alternative hypothesis is this, j equal to 1 to up to m, or I'm writing beta I, so let's say I. Okay, so uh, now what is basically the meaning of it? So uh, if the null hypothesis, so when do we reject or accept the null hypothesis? We find its test statistic. Okay, so in the last one we have done for b not b1 etc etc, but here we will do just like one, and then we will do all by this. So this one is equal to, we will have that, and then let me use I have used I everywhere. Okay, so what is the t statistic? The t statistic is nothing but just bi's minus uh, this value. So this value is 0. So like z minus z dash or whatever z dash you are taking. So here we are taking 0, so it takes basically 0 divided by standard error of this. So now based on this, we will take the decision. So we will uh, reject h naught against h1 at alpha level of significance if that p value will be less than alpha. Okay, so we will reject that h naught if p value is less than alpha. Now, rejecting h naught will be what? Rejecting h naught, that means beta i's are not beta i's are not equal to 0, right? So, uh, let me say y is equal to, let's say, the model we have got, right? So model we have got here is it is minus
It is not equal to zero, man. Will reject it.
uh, let me just repeat it. Just I will
Okay.
write it and repeat it. Okay, 0.860 plus 1.11002 x1 plus 4.85 x2 plus 0.2787 x3. Okay, okay. Now what we have is that if you try to see from here, okay, can you say any beta I equal to 0 or is nearby 0? So just this one is nearby 0. But
Is
if
nearby zero.
okay, but if you try to see, this is 11, this is 4.85, this is so far from 0. But the hypothesis says that we need to find the t statistic pi divided by the standard error of it. So if there is very much standard error, so what will happen? The t statistic will be smaller. T statistic will be smaller. That standard error is very much higher. So that means it is really not in, like, affecting the model. It is just there. So standard error is so much, so it is not helping in our modeling because there is so much error involved. So here you can see that there is so much error for this estimate also. The error is 11. For this also, the error is more than the estimate, and for this also, the error is so much. So, what it says is that if this value, after finding this value, so we try to find this and we try to find t at this point. So, we will find t at that point. So, that will be 15, 20 minus 4 minus 1. So, that will be t15. Okay. So by rejecting that, so here what is our result? Let me just copy paste it here. Okay. So what it says now, that for this the p value is uh like for the 95%. Okay. So uh this one is basically 95% and this one is more. only this one there is double star, and only this value is less than 0.05. So only uh, the p of nb is less than 0.05. All other p values are greater than 0.05. So we write
In
that.
this case, the standard error is 12 point. What is that? Standard is 11.27.
Yes.
So we will divide the
Estimate.
x1
Hmm.
with that 11.11 divided by 11.
Hmm.
So this is already around 1.
Yes.
This is minus 1.
Hmm.
So here we will be, and the alpha is p value is 0.05 less
Yes.
than.
Yes.
So here we will be rejecting it or accepting.
You say.
The model says
Hmm.
the model says that to the decision rule,
Hmm.
what we have seen is the decision rule is what it says. Just a moment.
I think if it is less than 0.05, then we are reject H0,
Hmm.
and if it is greater than that, we will be accepting the alternative hypothesis.
No, rejecting the null hypothesis means the accepting the alternative hypothesis. So if p is greater than 0.05, that means
Then we are accepting
we
H
we
naught. We are accepting H naught. No?
yeah, and we do not say it. I don't know why, but we say that we uh, cannot
Reject if it is less
reject
than the alpha.
h naught, and here we say we reject h naught.
Right.
Okay. So now basically rejecting or accepting h naught, all matters is that, like, if I will say in statistic language this is reject or accept, etc. But if I say in general language, the simple thing is that whether that parameter is important for our model or not. So if it is less than 0.005, sorry, is less than
Point zero
0.05, that means it is important to model our parameter. So that means number of run is dependent on number of balls. But if it is greater than 0.05, that means it is not important for our parameter. I am just modeling it. So it is not making our model any better. Okay, because it is not good, means these parameters are really not good for our model. So that is the simple thing. If you try
Mean
to
it is
understand
it's
in that.
mean it is otherwise, ma'am. If it is less than 0.05,
Hmm.
then we will reject it. Mean we are not counting this for our modeling.
If it is less than 0.05 p value, then we reject h naught. What
Yes.
is the meaning of rejecting h naught? Rejecting h naught means that beta I is not equal to 0. Beta I not equal to 0 means, let me tell you in this way. It is beta 1 x1 plus beta 2 x2 plus beta 3 x3, and then we have beta naught. Okay, interceptor.
Okay.
Now if beta 1 is not equal to 0, so that
Yes.
means our y will be beta 1 x1. If it is equal to 0, it is equal to 0, it is equal to 0. What will happen at the end? The only model I have is that y1 is equal to beta 1 x1. These values will not matter. So that
Okay.
is the meaning of rejecting or accepting. So at the end, when we say that we cannot reject h naught, that means uh, We cannot reject h. Let me not
I
write this.
mean, we are accepting the errors.
Yes, so we cannot reject h naught, means those beta i's are equal to 0. So at the end, our model, before that, our model was y1, y is equal to beta 1 x1, beta 2 x2, etc. But performing after finding its summary and p value, our model changed to this. So we do this a lot, because in the real life, what happens is that you have one variable and you may have 10 variables. So you firstly do the regression and then remove all those parameters for which p value is this. So we are just going to remove all those for this, for which they are not putting any significant impact on the model.
Okay.
Is it clear?
Yeah, ma'am. That is.
Is there any issue now?
No, no issue, ma'am.
Okay. So this is in basic simple language that we in the starting, because we have no idea that whether it matters or whether it does not. So what we do is that we just do the regression, and then one by one we just see that whether it is good or not. Now if you try, now this is in the time of 0.05. If you try, if you will take in the point 0 1. Okay, so if you will try by 0.01, so that means p value needs to be less than, sorry, not 0.01, point 0.1. If you try by zero point 0.1, so you can see that p value is less than zero point 0.1 for here also. These thing all done for 95%
Point one
significant.
mean 90% confidence
Yes.
level.
So point one is 90% confidence interval. So if you are doing your work with 90% confidence interval, then you can take this. There is no issue. So you can say that,
When our result will be having more error if it is
uh,
90% of
yeah,
confidence.
so result will have more error, and then we can say that okay, we are accepting this. But when you don't know that, okay, so like in real life you may need to do these things, like we are taking this, or let's say you may think that we can get more data, and maybe according to your point of view this variable is also important. So right now if it is not important, you can collect some data and you can say that it is almost nearby zero point 0.1, so we are taking this value also. So that is way you can do. Another thing you need to see here is that when we have done this, okay, so it is there also. When we have done this, you can see that the correlation with number of sorry, the np, whatever value was that, was also high. It was 0.42. But here, uh, the NP is 0.43387. So NP is also rejecting. So what you can see is that even if you think that the correlation is high, so it will, one will be dependent on other. So that is also not a true case. So if even if the correlation between two parameter is high, so then also, because correlation we are just uh, doing that multiplication in that linearity form, and it may not happen that one is really dependent on other. Okay. So this is regarding the testing of hypothesis, and the next thing and the last thing we will go through on this lecture is confidence interval. So uh, so now, as I have said earlier, So to find the confidence interval, all we need to do is that uh, we need to have that in between that uh, 1 minus alpha percentage. So we will have this minus t alpha by 2 at that n minus m,
Okay.
and then uh, and I'm just writing s e j less than or equal to t alpha by 2 n minus m, and that needs to be 1 minus alpha. So this will be our confidence interval. All we need to do is that multiply. Okay. So the confidence interval in the last lecture also we have found by using that confint, and we have given the level as 0.95. So and we're gonna replace this by our model. So this one is our confidence interval. So for the intercept, the confidence interval is this. For the number of balls, the confidence interval is this. And for all these, the number of the confidence interval can be given by this. So it is 2.5 and 97.5%. Okay, so this was all regarding the lectures for this week. Now we will do some questions. So there is one scenario,
Before,
and
ma'am, just I wanted to bring your attention again. I just want to, if we could open the explanatory, the notes, the lecture notes of week 11, page number 54. I think I have some wrong conception in
uh,
this. When we are accepting the H
uh,
naught,
let me just open it. Okay.
yes, ma'am.
Uh, uh, which
Page
which
number
lecture?
54.
Page number
Page
50.
number 54. Yes, ma'am. 54.
Uh,
Okay,
just
lecture. Actually, I was talking. This is complete note. The transcript it is, I think so.
yeah. So
Page
you
54.
you can
That
tell
lecture
me.
number, I will just tell the lecture number, ma'am.
Hmm,
This is lecture number 49,
okay.
test of hypothesis.
Hmm,
And here it is, when H naught is accepted, it implies that the explanatory variable xj can be deleted from the model.
uh,
Mean the contributor variable is deleted.
uh, here.
Just a moment, ma'am, let me go. Yeah, here it is.
Okay. So what it says is that when h naught is accepted, it implies that explanatory variable xj can be deleted from the model. Yeah. So what is the problem?
However, I mean to say that, say, ma'am, this consider the y is x1, b beta 1,
Hmm,
and b. There here are three variables.
hmm,
So suppose the contributor is beta 2 or beta 3 maybe. If we are accepting here the h naught
hmm,
when we are testing it, and accepting it does mean that we are deleting it.
hmm,
Mean the contributor is suppose only beta 1 is there, beta 2 is not there. Uh, or vice versa. Suppose B2 is 0,
hmm,
beta 2 is 0,
hmm,
is accepted. So beta 2 0 in the population is in the population, and beta 2 is not significant.
hmm.
Accepted mean it is more than alpha, the value.
Yes, yes. So beta 2 equal to 0. So H naught is accepted. H naught is accepted means that beta will be equal to 0. So if that beta will be equal to 0, what will happen to beta x? So
Okay,
if beta 2 is 0, beta 2 x2 will also be 0. So that beta 2 x2 will be removed from that model,
okay,
isn't it? So the example is that H naught is accepted. So H naught is what? beta 2 equal to 0 is h naught. So he's not saying that, so he's saying that I have just done for that beta 2. Uh, Now in H naught, beta 2 equal to 0 is accepted. So that means beta 2 equal to 0 is there. So beta 2 equal to 0 is in the population, and now beta 2 is not significant. So when beta 2 equal to 0, so if I
Okay.
will put it in the model, what will happen? It will be just not there because multiply by x2 will be 0.
Yes. Now I just got something.
Okay. So it may create some confusion, but do not like, rather than just confusing on that p and etc. Just what you need to do is that find the p value. Okay.
Okay.
After finding p value, if it is greater than 0.05, all you need
Mm-hmm.
to do is that put the beta equal to 0, because whenever it is greater than 0.05, we
Mm-hmm.
accept the h naught. Accepting the h naught means that beta equal to 0. Beta equal to 0 means it is not significant for our model. So it is not
Got
contributing anything to our model. That is why we want it to 0. That remove it. That why do we do that much of calculation if it is not very important?
it.
Simple.
This derivations will come in the examination, ma'am? Yes.
No, derivation will not come, but just revise it so that you can understand it well, because
Yes, yes.
you may have some questions from here, but derivations does not come in the exam.
Okay.
Did you get that pattern? Because I think they take the exam on the computer based.
Okay.
So computer
So,
based, so most probably there will be multiple type choice questions only.
right. I was just trying this.
In that, I have a question. Is
Yes.
in that case, online exam conducted.
Hmm.
So, what should the R software will be available in the
Mm,
examination or not?
I don't think so. The R software will not be available. You will have that models, because if it is, it will be available. I think like the questions we do in MCQs, like in the assignment, they ask that what is the uh, let's say for a scatter plot. So what do you want to, what is the uh, basically what to
Then
say,
it will be very
syntax,
difficult,
what
ma'am.
is the
Okay.
syntax for that. So if they will give R software, you can find the syntax very easily for the from R software.
Okay.
So
Okay.
Yes,
Okay.
but
Means only the multiple choice will be given. I think we have to answer on that matter only.
yeah, I think because they take the computer based, so there will not be writing thing in the computer based program exams. So they can give the question, you they can give you the notepad like whatever we do in the gate exam, net exam, etc. But the proof kind of thing will not come.
but but going by the
Another.
last email, ma'am. I'm just sorry to be interrupting here.
Huh.
As per the last email we have received regarding examination,
Hmm.
it has been said that there will be some proofs, and multiple choice questions will also be there.
Hmm.
Slightly writings will also be there. Yes, no, and filling the blanks. Small
Okay.
writing of answers will also be there.
So maybe they have changed the pattern, because till now all I was saying is that because there are NPTEL centers and then they people just go there for examination. So if they are taking that, so I don't think they will take for the long proofs. So
Yes.
that most probably will not come, but just for so you can just go through it once, but the long proofs most probably will not come.
I mean, what was my concern was, man, that
Hmm.
see this course is related to R software,
Hmm.
and if R is not available,
Hmm.
so at least the modeling purpose. Suppose we are feeding the commands, the
Hmm.
codes if we are applying.
I know, but what I have understood, like in the last exam, because I'm taking the R software, I have taken this like part one of this R software in my last semester. So there also they have said that they are not given the R software, and that is why, like, whatever questions they give or whatever question I try to solve here, so we just say that you need to remind that commands. I
Because as you are aware, three questions I have pointed out,
hmm,
those have answers, wrong answers,
hmm,
and we have also verified in this class, in these classes,
hmm,
in
hmm,
previous classes,
hmm,
and we found that the answers were not correct, which were
hmm,
posted and
hmm,
evaluated by
hmm,
the researchers. This is what.
hmm,
So, but if we put the solution which was provided by the
hmm,
NPTEL,
hmm,
the answers were different.
hmm,
However, I have not posted my answers. I will post it because I am in field nowadays.
hmm,
So I'll post my correct answers, which we have verified.
hmm.
So if the R is available, then it becomes very easy. All the assignments becomes very easy.
Yeah, but see, I'm just the TA for these classes. So whatever assignments they give, whatever question paper they give, and whatever the pattern they take, that is governed by the instructor and their TA supervisor. I am
Okay.
just for this, so I do not have any contact neither with the instructor nor with the TA, the Prashant sir. I do not have any contact with them. So if you have questions related to exam queries, so I all I can do is that I can help you with understanding the concept. But if you have questions related to exam queries, then you
No
can
problem.
ask them.
Please continue with your
Okay.
examples.
Okay. So
Yeah, one question regarding this.
yeah.
The hypothesis we
Hmm.
are just three type of hypothesis we generally come across. One is less than some values.
Hmm.
One is greater than some values, and
Hmm.
another third is a inequality.
Hmm.
In this case, we had equal to or unequal.
Hmm.
So in this case, what we do, we take the intervals. In the both two-tailed solution
Hmm.
are been considered. So in this case, we are considering that when alpha is taken zero point zero 0.05, we
Hmm.
are not considering it as 0.025. We are just considering zero point 0.5, zero point zero 0.05 only. Means alpha by 2 is not considered. Whereas in the interval, we are considering the same thing. How it is related, means it is auto calculated by the R software, or it is something like that.
No, okay. Firstly, you need to see that whenever we have this basically uh, whenever we have this type of hypothesis, it does two tail test. It never does just one tail. Okay, so if you have three types of hypothesis as you have said, so one is beta one equal to zero, and h1 is beta I not equal to zero. Another can be beta equal to zero, beta I, and then alternative can be greater than zero. When it is greater than zero, we will take right tail values of alpha. When it will be less than 0, we will take left tail. But when it is not equal to 0, then it is taking the R software itself will take the two tail test. It will not take one tail test. Another thing is that the reason why we are choosing here is not equal to 0, because all we need to know is that whether our model is dependent on x or not. So let me say that y is equal to beta 1 x1. So if that beta 1 is equal to 0, uh, or let me just put this, if beta 1 equal to 0, what will happen? It will be y is equal to beta 2 x2. And if beta 1 is not equal to 0, so if it is not equal to 0, we will have this model beta 1 x1 plus beta 2 x2. Why we are taking equal to and not equal to? Because that all matters for our model. So if y is let's say uh 3x1 plus 2x2, or let's say minus. Okay, so now our concern is not that whether it is greater than 0 or whether it is less than 0. If it is greater than 0, if that beta I is greater than 0, that means when that xi will increase, that yi will also increase. Okay. When that beta I is less than 0, that means when that xi will increase, yi will decrease, because that's how they are dependent. If, because let's say here, if there is yi beta I xi, so if it is beta I greater than 0, that means this one is increasing, this one is increasing, and in the below case there is just opposite. So for us it does not matter on increasing of one whether other one is decreasing or increasing. All we need to know is that whether one is affecting the other or not. So if one is affecting other, that means beta I is not equal to 0. So this is what we need to check, if whether one is affecting the other or not. If that beta is not affecting our yi, that means that beta is equal to 0. So whenever you do the hypothesis, you create the hypothesis according to your work. In our work, all we need to know is that whether that x parameter is really changing our y or not, whether it is significantly contributing to model that y or not. So here, that is why we have taken the hypothesis as equal to and not equal to. If you will take some other hypothesis, let's say the light bulb, whenever we take, so we take lifetime, so we take lifetime equal to 5 or lifetime greater than 0. So sorry, lifetime greater than 5. So whether its lifetime is 5 year or greater than 5 year, if it is less than 5 year, we do not care about it. So you need to create the hypothesis according to yourself, and if your hypothesis is one sided, then your alpha will be uh, 0.05. If it is two sided, your alpha will be like 0.25 in the below and 0.975 in the above.
Okay. Okay.
Okay. Uh, so here we have one scenario. So what is the scenario? We have some agriculture experiment, and we want to see. We have a crop yield, and we want to see that how the independent parameter are affecting it. So first is that amount of fertilizer used. The next is irrigation level, whatever we have in centimeter. Next is average atmospheric temperature, because that also matter for the crop. And here is the area under cultivation. Okay.
Hmm.
So the experiment done on that. So it, after fitting the model, is this. So we have this fitted model, and the thing, these are that standard error are moderately small. Obviously the OLS properties are holding, so residual sum is nearby 0. The next thing is that hypothesis testing on slope yield the large t statistic in absolute value for those that are truly different from 0. So basically the t statistic value will be very high for those which are different than 0. So here also you can see that the t statistic value is higher for this, which is for which beta is not 0. Okay. So now the first question is that to make the scatter plot of all these, what do we need to do?
Pairs yx. How many variables are there? Three, four
Four.
variables.
Yes.
Four. That's first one, ma'am.
Yes. So what we need to do is that y, and then we will do x1, x2, x3, and x4. And in that main, you can write like whatever you want. Okay. Uh, the next question is that Which of the following R commands fits the multiple regression model that predicts y from x1, x2, x3, and x4?
Fitting last one.
Last one.
Last one. Last one is not fitting.
Yeah, so the first one is the correct. Here you can see
First
that
one, yeah.
I have
This is
done
why.
y and
Uh,
then this and then
First one, yeah. Next one.
uh thing is next thing is that y is equal to 10 and then all these. So what does this 10 intercept 10 represent?
Intercept. No? There is expected yield when all procedures are zero. What does the intercept time represent? Here there is impact of fertilizers. That is that is expected yield when all.
It's number one.
First
Expected
one
yield.
then.
All predictors.
Average yield at 20.
Number one only.
Yes. So when all others are 0, so y
0.
will equal to 10. So this is the expected yield when all the predictors are 0. Okay. The next question is that under the fitted model, so that is the calculative part. So this one is just 10
50, 22.
and then we need to put from, okay, let me just make it closer to this so that we can see all in one screen. Okay. So it is 10 and then 2.5 times 8.
8,
So I
15.
think first one is the correct one and then
Yeah,
it has solved already.
yeah, this is 55. 8, 15, 22.
Okay, so
So
that is not the basically question. All you need to do is that put the values. Okay. So here, so which statement reflect a standard property of residues in OLS regression model?
sum of residues is 0. Sum of square residues indicates the sum of absolute residues. Second one, sum of residuals.
So
Yeah,
this is
second one.
the property for the OLS regression. Uh, which of the following model is not considered as a valid regression model?
Linear in parameters. So this will
Second one.
logarithm is not there.
Yes.
Logarithmic will not be.
No, I think third one is x4 square is there.
A square will
It's
be there. Is two logarithmic.
I think x4 square, that is not linear. That is not linear. I think. Yeah. No, no. It just. Uh,
What is its
yeah.
property
That.
when it is not linear?
Yeah.
So it will be B or C.
Logarithmic scale is there.
It's C. It's C.
Okay, so it will be both because what is the property basically when you try to take the derivative? So that needs to be independent of it,
Yeah.
right? Okay. Okay. Uh, the next one is that assume the estimated coefficient of x3 is 0.75 with the standard error of 0.15. What is the t statistic for testing the null hypothesis beta 3 equal to 0?
Means 0.75, 0.15, minus zero point 0.5. That is 5.
Which one will be the correct option?
Minus b means plus it will become. So plus 5. This one 75 minus 5. First one it would become a
Yeah. So t statistics is nothing but that
minus b by
bj
standard error. That
divided
is
by standard error of
standard error.
bj. So it will be minus 0.75 divided by 0.15. So it will be minus 5. Okay. The next is for the coefficient of x3, a 90% confidence interval is computed as minus 0.95 to minus 0.55. Which
0.55.
interpretation is correct?
So x3 and y is between the increase of 1.5. So it's 5 between 1.95. C members is not an important value.
Okay, so 90% of the value fall
Will fall
between.
between uncertainty if we take 90% the coefficients is talking coefficients. Right. It's just solution interpretation is confidence interval is 0.95. We are 90% confident with full effect of x3. Also the coefficient of x3.
It's B only.
Y is between the increase of 195 and a decrease of 0.55 minutes.
So
So
it
it
will.
is x3 man. That's
Okay, so we have that, and there will be a point estimate,
yeah, it will be
and then 90% values will lie in between this. Okay.
Okay. Yeah.
0.95.
Yes. The next one is assume that fitted model is stored in fit model, then which command will return the fitted values?
Our model called fit model. Fit model. Residuals will come on return fitted values. Fit model coefficient predict fit model type. Assume that the fitted model is stored in the R object called fit model. This first one,
Yeah.
fitted fit model.
So we have done it here also. We have just done. Okay.
And one that this to answer the assignment, the recent assignment,
Hmm.
the 11th.
Hmm.
There's a question again. There was a dilemma. I was just working with
Hmm.
this again. Just I'm discussing myself.
Hmm.
The H naught value has come as 12.651.
Hmm.
So we have to, because it is higher, so we'll accept the null hypothesis, and the important variable will not be, the
Hmm.
concerned variable will not be.
Hmm.
Just mean if we are accepting, if we are rejecting the H naught, then the variable is important.
Well, let me just see that. Okay. So which question?
This 12th, I think so, 12th number.
Okay.
12th, May, 13th, ma'am, 13th, yeah,
Okay.
13th.
So what
So
is saying
suppose
that?
for if we calculate it, it will come at 12.651
Okay.
right now. So now we have to accept it because it is more than the alpha
No. This is T statistic.
t statistics. Yeah,
Yeah. So what you need to do in that case, have you fitted that model?
yeah, yeah. I have fitted. I've done it.
So regarding that 12.6, did you get that 12.651?
Yes, yes.
Then nearby, what is the p value of it?
P value. Then I have to go back to my R model.
Yeah.
Okay, okay. Then I'll go back. No
Okay.
problem.
So you need to see that p value, or what you need to do is that if you want to see just based on that, so what you need to do is that uh, just go through t table values and uh, okay. So what it is saying firstly, uh, null hypothesis and conclusion. Okay, so I think they are just taking for the 95%. Okay, so their t table, it is, where is the table? Okay, so there you need to check according to your value because the value is that 15, right? So I think it is very much higher. So it is gonna take so it what you will do is that you will reject the null hypothesis.
And then the variable will be important for.
Yeah. So when you reject the null hypothesis, that means beta not equal to 0. When beta not equal to 0, the multiplication of it will come. When beta equal to 0, the beta 3x3 will also be 0. So when it is
Okay.
0, so in equation it is
Then it
not
will
gonna come.
discard. Yeah.
Yes. So when in equation it is not gonna come, that means it is not an important variable.
Okay. Okay.
Okay. So
So
if you want, if
this.
you have found, because in the R software you have that p value. In the real life, if you are not finding that p value, all you need to do is that find that t statistic, go to that t table, and in that t table you need to find this. What is your
Okay.
degree of freedom? According to degree
Degrees
of
of
freedom,
freedom. Yeah.
you need to find that value. If your value is greater than this, then you can just accept it. But in the R software, since you are doing, you will have that p value also. So regarding that p value, just check. I think it will be less than 0.05, obviously. So on that, you can accept or reject.
Okay. T statistics. Next one is.
Okay. So moving to the next question. In the fitted model, the coefficient of x3 is minus 0.75. So what does this indicate?
And T so point is this is 75. No effect of field. It's a decrease of field 0.75.
Yeah,
B.
yeah, B. This one is, I think, last question. So which command will create, okay, I think this is the repeated one. This not right. Okay. So these are the questions I had. Okay. So you can ask if you have any question. And for the last class, like there is an extra class I will take on 16. So you can create your set of questions if you have any. Or otherwise, I will make some questions, or I will try to that whatever happened in that these 12 weeks, we will try to just go through a little bit of it, a little bit of important points. Uh, and
Okay.
that's it. Okay. Okay, so thank you for joining, and I'm ending the class.
All right, ma'am. Thank you very much.
Thank you.